Okay, let's continue with the session. Our second speaker is Georgios Styliaris from the National Institute of Quantum Optics. He will be talking about quantum circuits assisted by LOCC.
Thank you, and thank you all for coming here today. And a big thanks to the organizers for putting everything together. So it's a great pleasure to be talking about our recent work where we put together quantum circuits and local operations and classical communication. And in particular, we look at questions related to transformations and phases of matter. So let me start from the beginning. The theme of this talk is locality in quantum physics. And in particular, I will be interested in the classification of states and operations that arises from locality considerations. So however, what local means can be very different depending on the context. So if one is interested in quantum information, then the corresponding paradigm is that of local operations and classical communication. And the classification is the one arising from entanglement. So here I want to highlight first the obvious fact that measurements are very important in this framework. And also that although a well-defined notion of subsystems is needed, there's no notion of how close or far the different subsystems are. So on the other hand, one can adopt a many-body perspective, where locality refers to locality of interactions, as is the case, for instance, in local Hamiltonians. And here, the classification is that of phases of quantum matter. Notice here that measurements play absolutely no role, but the notion of geometry is needed, how far or close are the different subsystems. So a motivation behind our work is to notice that elements of both of these approaches come together rather naturally in near-term quantum devices. So what I mean by that is the following. So for instance, noise considerations limit the depth of the circuit to be some small shallow depth, and there's an underlying geometry since gates have some locality. Moreover, which is a very important fact, one has access to measurements and classical communication. So this raises the question, how can one use, in a creative way, measurements and classical communication to aid in certain tasks? So in this talk, the first thing I will do is to introduce such a framework, which I'll denote as you see, which puts together quantum circuits and local operations and classical communication in a formal way. Then I will explore implications of these definitions and show you that assistance by LOCC can reduce certain large depth quantum circuits to just constant depth. And the point here is that this can be done deterministically, even though measurements are involved. And then I will suggest an extension of the standard classification of topological phases of matter based on this notion to include LOCC. So, okay, let's start from the beginning. So the point here is to introduce deterministic transformations that combine quantum circuits and LOCC. So my quantum system, I consider it to live on a lattice, either in one or more dimensions. And nodes are qubits, and links denote nearest neighbors. So in that framework, I can define what is a local depth L quantum circuit, which is just a unitary of L layers. And each layer can look like that, then the next one like that, and so on. So now the point is to define a state transformation arrow starting from a state phi that will add on top of this structure LOCC. So I start by adding ancillas, which are initialized in some product 0 state. And I'll consider, since I want to be careful with locality, that ancillas belong to a given site. Then the first step of the protocol to define the arrow will be to take a finite depth quantum circuit just like before, and add in between the layers some local interaction between system and ancilla. So here you note is this local interaction between system and ancilla, then the first layer of the quantum circuit, then yet some local interaction, the second layer, and so on, until my depth L is reached. So this is the first unitary part. Then we allow for measurements that happen over ancillas and classical communication. And here classical communication is unrestricted in the sense that the measurement result happening somewhere is communicated to every other party. Then the third step is some local unitary correction, where it can crucially depend on the measurement outcomes. And the last part is to discard the ancillas. So if there exists such a process such that my output state is a state psi and pure, then I will use this state transformation arrow. And here, very importantly, I want to restrict the measurements to happen all simultaneously. And notice I don't want to post-select, of course. The results will be deterministic and a pure state. So, okay, now we'll explore implications of this definition. But before going there, I would like to remind you of something that will turn out to be very important and is a very simple fact that goes by the name causality. So what I mean by that is consider some local observable OJ and evolve it in the Heisenberg picture with a local quantum circuit. Then it's very easy to see that some of the gates will cancel, and what one is left with is a light cone. So what this implies is that if you start from a product state and you evolve with such a finite depth circuit, then the correlations that can be created in that state can be at most at distances of twice the depth. Okay, and this fact will come in handy right now, because now I'll go back and want to explore what is achievable in my framework. And for that, I want to consider one dimension and the GHZ state. So it's very easy to check that in this state, correlations do not factorize. And just from the previous consideration of causality, this implies that if you start with the product state, it's impossible to create it with a finite depth circuit. However, it holds that if you start from a fully product state and you use local operations and classical communication on top of the finite depth circuit, just depth 2 is enough to deterministically create the GHZ state. So the point of this example is to show you that local operations and classical communication enlarge the set of achievable states, and in particular, allow for states with long-range correlations. So, okay, what else is achievable in this framework? So the next target, the next natural target, is states with more complicated correlations, and in particular, topological correlations. So now let's go to 2 dimensions and take the toric code. So it's very well known that you cannot create the toric code just with any finite depth circuit from a product state. This is a consequence of the topology of the state. However, if you allow local operations and classical communication, just finite depth is enough, and this can be done deterministically, like before. So once again, the point is that the achievable states include also states with topological order. And the idea behind this construction is in fact simple, relies on a construction that goes back to 2005. And the idea is to express the toric code as a stabilizer state and enforce the +1 eigenstate using measurements. So, okay, at this point, you might wonder that in fact the framework is too strong and everything trivializes, but this is not the case. And the way to see this is to consider properties of the states that can be achieved. So it turns out if you can transform a product state to a target state psi in this framework, then this state, the target state, has to obey an area law. So what this means is that if you split the lattice into parts A and B, then the reduced state on A can have Remy entanglement that scales at most as the boundary of the region. And this holds, in fact, for any Remy entropy for any index alpha. So, okay, I've shown you some examples so far to convince you that interesting states can be constructed and shown you the framework is non-trivial. So now I would like to generalize and say something more general than just examples. And for that, I would like to adopt the perspective of phases of matter. So let me first remind you a few things about quantum phases in one dimension. So in one dimension, a phase is just an equivalence relation between sequences of states. And the reason one needs sequences is because a phase is something that makes sense in the thermodynamic limit. So here the index of the sequence just denotes bigger and bigger system sizes. So the standard definition states that two sequences are equivalent if they're connected by a local quantum circuit up to some error. The depth of the circuit is almost constant. In fact, it scales very, very slowly with the system size, like a polylog. And the error of the conversion should be vanishing when the system size grows bigger and bigger. And the standard classification is carried out in the framework of matrix product states. And the result is that all translation invariant matrix product states that correspond to the same degeneracy are in fact in the same phase. So now my goal is to take this definition and result and try to extend it to include local operations and classical communication. So I want to introduce a classification of phases that incorporates LOCC. And the way to do that is rather simple. So the idea is to extend the equivalence relation by using the arrow of state transformations I defined previously. So carrying this out, one reaches the following definition, that I want to state that two sequences are equivalent now if they're connected both on the direction from psi to phi and from phi to psi with my state transformation arrow. We allow again for some error and a finite number of LOCC rounds. The depth to make connection with the previous definition is exactly the same, should be some polylogarithm of the system size, and the error should be vanishing as the system size grows bigger and bigger. So notice that this is really an extension of the previous definition in the sense that if one does not include ancillas, then there is no LOCC, and this definition reduces to the standard definition. So it's really an extension. And now I can state the main technical result of our work, which is the following. So it is that all translation invariant matrix product states with some fixed bond dimension are in the same trivial phase under the equivalence that includes local operations and classical communication. So here I want you to notice that we do not restrict to matrix product states with the same degeneracy. And what this result means in somehow simple words is that if you start from a product state and you're interested in converting it to the thermodynamic limit to other states, every matrix product state is reachable. So it's a reachability result in the thermodynamic limit. And of course, vice versa. Starting from such a matrix product state, you can convert it to the trivial state. So, okay. For the remaining of my talk, I would like to consider something slightly different, and this is implementing unitary operations with the resources I'm considering, which is finite depth quantum circuits and LOCC. And let me explain what I mean by unitary operations. So previously, I defined the state transformation arrow, and it was very important that my initial state phi was fixed. So now I want to ask what happens if I don't want the input state to be fixed. Then in general, if you fix the transformation protocol, this defines a quantum channel. And generally speaking, if you input some pure state, which is not fixed, some arbitrary pure state, then the outcome will become mixed. So now the question is to try and build deterministic unitary transformations with the resources I'm considering here. So in other words, I want the action to map pure to pure states for any input. So this is the difference, the any input part. And since this is a slightly bit more technical, let me first announce the results before giving you the construction. So the take-home message for this part is that I will show you a class of unitary transformations which can be implemented deterministically with finite depth and LOCC. And these unitaries are not finite depth quantum circuits, they go beyond. So let me give you a flavor how this is done. So the key idea is to take the channel state duality, but promote it from a mathematical tool to a physical process. And this is what I mean by that. So here in this sketch, I have bell pairs in the phi plus state. And if you act with a unitary on half of the pairs, this creates the corresponding choice state of the unitary. So now I would like to turn this choice state to the action of a unitary over some input state phi, which is unknown. And the way to do this physically is to implement measurements over part of your choice state and your unknown input state. However, this method has some challenges. And the first one is, since I want to implement it in my framework, I would like to be able to create the choice state in the first place. So this is the first problem I need to solve. Then even bigger problem is that for this method to work, in fact, post-selection is needed in general. because for the unitary to act on my state phi, I need to post-select the measurement on the phi plus result. But this will happen only with exponentially small probability, generally speaking. So I want to avoid that. And the last challenge is that if an unknown measurement result happens, I want to be able to correct it locally. So it turns out that all of these problems can be overcome, at least in particular cases. And such examples are given by certain stabilizer states, such as the GHZ and the toric code I talked about earlier. So the idea is to use the so-called locally maximally entanglement states that were introduced in 2009. And it turns out, using these ideas, you can turn these states to the corresponding unitary operations, U, GHZ, and U toric code. And the GHZ example looks like that. And the point that I want you to notice here is that if you act with this unitary on a fully product state, you will obtain up to local equivalence the GHZ state. So now, using the previous argument about light cones, immediately it follows that this unitary cannot be implemented just with a quantum circuit alone. The toric code unitary is slightly more complicated, so I will avoid giving the expression, but the point here is once again the same. If you act with the toric code unitary on the zero state, you will obtain the toric code. And the claim is both of these unitaries can be deterministically implemented with the resource I'm considering here, and in particular, that is with some finite depth and just 2 rounds of LOCC that includes simultaneous measurements and local corrections. So, conclusion, these are unitaries that are not finite depth quantum circuits, but can be implemented deterministically with the resources I'm considering. Okay, and with that, I would like to conclude by summarizing and mentioning some open questions. So I've defined the state transformation arrow, and I've given you some examples of states with topological order and long-range correlations that can be created. But what is still missing is a characterization of this transformation, rather generally speaking. Moreover, I've given a rather general result in one dimension about the classification of phases, which includes local operations and classical communication. But this is in one dimension, and then this raises the question, what happens in more dimensions in general? And it was recently shown that even non-abelian topological phases trivializes. There are certain examples of such phases. So it's not only abelian cases like the toric code that trivialize. And of course, this raises the question, which is the topological phases that trivialize up to this extended equivalence with local operations and classical communication? Thank you very much.
Thank you very much. Please come here for the questions.
Thanks for the great talk. I think that was a really nice synthesis of a bunch of trendy topics in condensed matter and many-body physics. I was wondering, what is the main sort of technical contribution of your work? Because I know this like GHZ unitary was known for at least 10 years now by Suori and Pham, I believe is the first time they introduced it. So I was just sort of curious what you see as that.
So you're right, the examples are well known, and the point was to motivate what is doable in this framework. So the technical result is this one. It's about matrix product states. So this is very general and includes all these examples. And the tools here are to use the so-called RG fixed point of matrix product states and show that the recipe works out in the end. So the resources are enough if you use the RG construction to get any matrix product states. So to answer your question, the contribution, the technical contribution is this one, which includes the GHZ state, for instance.
Okay, so does this, so how is this separate from like the area law? The fact that all matrix product states with fixed bond mentions a Bayesian area law?
So, okay, this is a good point. So this boils down to what I talked about before. So the standard classification is done, states are equivalent if they belong to the same degeneracy class. So this, more technically speaking, corresponds to some blocks in the canonical form of the matrix product state. And states with long-range correlations, like the GHZ state, and states with exponential decaying correlation are in different phases because they correspond to different degeneracies. So here, all this hierarchy collapses. So this is what is different. So here we can create states with long-range correlations, and we don't restrict to ground states necessarily.
Mm-hmm. Okay. All right. Yeah. Thank you very much.
Thanks for the great talk. I was wondering if you can replace the measurement and classical communication with just gates from some classical logic like synods that are allowed to be non-local.
Well, it depends how you define non-local. So I think if you allow all-to-all communication, so if you allow interaction all-to-all, then more things are of course possible, but I cannot tell you right now if the same results are obtainable. I'm not sure. So even the GHZ state, I wouldn't be able to tell if you can do it with finite depth and long range. So I don't know. This is a very interesting question.
So you have sort of two measures of the quality of the transformation, sort of like the depth of the circuit, that the quantum circuit that's required, the amount of communication that's required between the local parts of the system. Do you think that there's room there, or it would be useful also to consider the amount of classical computation that's required?
So is the question whether imposing, counting the complexity, if you want, of classical communication, if my result would be different, or are you asking something else?
I think that you said there were some, you talked about the complexity of communication. You said it was like 2 rounds of communication, or maybe.
Okay, yeah, I understand.
But my question is about the computation required to do it. So maybe, if you have to do some kind of decoding in order to correct, you measure some stabilizers, you have to do some decoding, maybe there's some computational overhead in that, and you may not want to have to perform that computation. So I guess I'm just wondering if you think that's a useful thing to add to the measure of this transformation.
So okay, let me say a few things, and then if that doesn't answer, please feel free to follow up. So here one needs to be careful not to transfer the complexity of the depth of the circuit to the LOCC part. So this is why, first of all, I want all the measurements to be able to happen simultaneously and not one after the other, because this would scale with the system size. So this is one comment. Then the other comment is, how do you figure out in practice, given the measurement results, how to correct? And I think this is what you're asking.
Yeah, exactly.
And it turns out this step is not hard.
So generally for this class, there's no problem with the computational complexity.
No, this is no problem. No, it doesn't have a hidden complexity. No, this is an easy part.
Oh, okay.
Because the correction is local. This is no problem.
Thanks,
yeah.
That helps.
Thanks for the great talk. So, so in the end, you show that you say that some non-billion topological order can trivialize in your definition, and I'm wondering for those models. So are you considering quantum double model, and also whether the braiding of those anion just not universal, and is it possible that for Fibonacci anion, which is universal, that it doesn't trivialize? And also, do you have any intuition that what kind of many-body phase don't trivialize in your classification?
So these are very interesting questions, but unfortunately, I don't have much to say. So we do not know very well. So there's some examples of non-abelian topological order. I don't know if they include all quantum double. Probably not, but I'm not sure. Our intuition is that probably what is impossible is chiral topological phases. But this is just a guess. We don't have a formal proof or anything. But these are all very interesting questions.
But in your example, you don't have a Fibonacci opinion, right? You don't have a computational universal model. Is that right? In the example of this paper.
Yes. Okay. So your point is?
My question is, in the example you consider in this paper, do you contain computational universal anion model?
Okay. This I cannot recall right now. I don't remember. You can ask. I think the author is in this room.
Thanks.
Hi, Malin from online asks, in the early part of the talk, it seems like you would need ancillas for QCCC to work. Could you comment on the number of ancillas needed and their roles?
Okay, this is a very good question. So let me say a few things. So here we allow, in principle, for ancillas to be as many as needed. However, in practice, in all the examples, the ancillas are linear in the system size. So you have 1 or 2 or something like that ancillas per site. And this also holds true in the general construction for the matrix product states, in the sense that the number of ancillas is dictated by the bond dimension. So, however, even if you're allowed to add unboundedly many ancillas, still the construction does not trivialize, because the area law still holds. So the area law result is independent of the number of ancillas. But of course, in practice, you want ancillas not to be crazy many.
There's 3 more questions from online. I'll let the chair decide if we have time for all of them. Okay, great. So Nathan McMahon asks, when constructing unitaries deterministically using QCCC, if you can deterministically construct U, can you also construct its inverse?
This is a good question, and I don't know right now, because this is a particular class. And I'm not sure, actually. This is a good question. I don't know.
Great. And Paul Herringer asks, have you considered any extension of your formalism to SPT phases?
Okay, this is also a great question, and very natural, in fact. So we are working on exactly that part. And so what I can say is there are many interesting variants of the definitions. This is what we know. So how are you going to impose symmetries on top of that? Because there are the extra ingredients of measurements and classical communication, of course, which you have to take the symmetry into account. And the way you do this is very important. So in certain frameworks are more trivial if you allow the symmetry to be weak. But the moment you make the symmetry stronger, then different inequivalent transformations occur. So this is a very interesting question. We're working on that. And yes.
Great. And then a question from Jun Takahashi. Is there an example of a state that doesn't trivialize with QCCC, but still obeys the area law?
So can you say again, if there is a phase?
So is there a state that doesn't trivialize in your model, but still obeys an area law?
Okay, I think a nice example here should be the W state. So it seems we don't have a strict proof for that, but the W state we cannot realize it with all LOCC being simultaneously happening, all the measurements happening simultaneously. And I think this would be an example.
Got it. Thank you.
Thank you very much.
Again, a couple of minutes to prepare the next speaker, and we restart.